Or goers, welcome back. Welcome to the Exam 3 review series. Today we're just going to talk about the Chapter 19 material, which is enolate chemistry. So it makes sense that the first thing we're going to talk about is enolate anions. Alright, so let's just zoom in over here. So, over here we have this aldehyde, and we can label the carbon that is adjacent to the aldehyde as an alpha carbon. Likewise, if there was one more carbon after that, we'd call that beta, and then after that gamma, and follow the whole Greek alphabet. But the carbons that are directly adjacent to carbonyls, or with respect to carbonyls, are called alpha carbons. And likewise, those hydrogens that are attached to that alpha carbon are alpha protons, or alpha hydrogens. So, we'll call back to Organic 1 when we were talking about acid-base reactions in Chapter 4. We were like, what was the trend for acidity? Well, we saw that when we went across the period of the periodic table, we were increasing acidity. But what was the rationale for that? Well, if we had a molecule like, let's just say, hydrochloric acid, so I'll just draw it over here, hydrochloric acid, we would rationalize the acidity of this molecule in terms of its electronegativity. So that chlorine atom is a lot more electronegative than that hydrogen atom, so it's going to attract more of the electron density to that side versus the hydrogen. So if I were to just draw that electron cloud, it literally looks like something like that, where it's partially negative towards the chloride and it's partially positive towards the hydrogen. When a molecule exhibits this like dipole nature, it's very easy for a base to come in and just pluck off that hydrogen, and that's the definition of an acid. Acids are, by their very definition, is molecular species that give off protons or give off hydrogens. And since this is an extremely electronegative molecule, it's very easy to do so. Likewise, let's use that same rationale with this aldehyde. These hydrogens, although not directly attached to a chlorine atom, they are directly attached to an electronegative functional group, which is the carbonyl. So this electronegativity pole, or this dipole moment towards, that carbonyl, is what makes these hydrogens on the alpha carbon very, very acidic and susceptible to be deprotonated by any type of base. All right? So it makes sense that we can use a base like sodium hydroxide to remove a hydrogen from this position. So let me just draw in the mechanism here. So if I had my hydroxide, and that's negative, and I have associated sodium hanging out, the mechanistic arrows in red show that we're going to take from the oxygen, that's going to take a hydrogen off of the alpha position, and then donate that electron density as a lone pair onto that alpha carbon. So the product of that step would be something that looks like this. And I'll just draw in the hydrogens for your reference. So, as you can see towards the right, I kind of alluded to it, but we have an alternate resonance structure for this enolate anion. So I can show the resonance arrows again in red. So I can take that lone pair on the alpha carbon, pushed in to form a pi bond, and then those pi bonds on the carbonyl are forced up to form an alkoxide anion. So the product of this molecule would be, this step would be O-, and then we have two hydrogens, 1 and 2. I know it's kind of ugly, but that is a double bond in the middle. Let me redraw that. Better. All right, so we have these two resonance structures. So enolate anions are resonance stabilized, so that's good. But let's talk about the equilibrium position of this reaction. So if we were to compare the two acids, so the acid on the left would be, those acidic protons of the aldehyde, but the acid on the right may not be as clear, but we generated water, because remember, that hydroxide base, it gains a proton after it deprotonates the hydrogen from the alpha position. So now I wrote the pKa's in over here, so the pKa of water is around 15, and the pKa of those acidic protons of the aldehyde are around 20. So the lower the pKa, the more acidic something is, and we will favor the equilibrium against the strongest acid. So we would expect an equilibrium that lies more towards the reactants, which is shifting towards the left. So the deprotonation of these alpha protons is not favorable. But we have an entire chapter dedicated to these types of reactions. So there's something else that we're missing to rationalize why these reactions progress. And that is, when we form, let's just say it's an aldol reaction, and we are under thermodynamic conditions, and we're forming alpha-beta unsaturated carbonyls. Well, those molecules are heavily conjugated, and heavily, we talked about conjugation being a stabilizing feature because we can localize these electrons over a broader region of the molecule. The formation of a very, very stable product will trump the effects of maybe like this negative step, which is deprotonating an alpha position. So if that didn't really make much sense, I can say it in another way. Basically, And this, even though this little step is not favorable, the formation of a very, very stable product at the end, such as like a highly conjugated molecule, will trump the effects of this because that's the driving force of the reaction. All right. So the equilibrium for the enolate formation is to the left, but we'll see that we can progress these reactions forward because we form very stable products. It's also resin stabilized, and these enolate anions can be used as nucleophiles to add into other carbonyl molecules, and that's what this entire chapter is about. All right. So let's just talk about this several considerations that we have with aldol condensation and the intramolecular version as well. So before we do anything, we have to define these 4 words. So let's just zoom in over here. All right. So these 4 words are, although you won't be tested on them, I think it's very important when you get each reaction to kind of like classify it. Hey, is it this? Is it this? Is it this? And if I use these words and classify it, I'm a little bit better off in terms of like predicting the product. So the first term is uncrossed versus crossed. So the term uncrossed basically just means that it's 2 of the same molecules reacting with themselves. So we typically see 2 equivalents written next to a reagent. Okay, so uncrossed, it's 2 of the same molecule reacting with itself. So one equivalent of that molecule is going to be the enolate anion, and then the other equivalent is going to be the carbonyl that enolate attacks into. So that's an uncrossed reaction. We see 2 equivalents. In a crossed reaction, those are crosses of 2 different molecules. So one molecule is going to be an enolate, and the other one is going to be some other molecule. That's the carbonyl that we're going to attack into. We don't know which one's which, but they are 2 totally different molecules. So we would see typically 2 different carbonyl compounds. So I said that 2 different carbonyl compounds. All right, the next set of words is directed versus undirected. Directed versus undirected. So directed addition is basically where one of those molecules can form one of those molecules has alpha protons that can be deprotonated to form the enolate, and then that enolate can be used to attack into something else that lacks alpha protons. So if that didn't make much sense, let's think about that. If one of my molecules has alpha protons and then the other one doesn't, the enolate can only be generated from that one molecule. Likewise, that other molecule that didn't have alpha protons has to be added into with the enolate, all right? So that's what it means by directed. You're specifically choosing reagents where one has alpha protons and the other one doesn't, so you can facilitate one set of mechanistic arrows in terms of a reaction. In an undirected aldol reaction, we have basically 2 molecules, and both of those molecules have alpha protons, and both of them can form enolates. So if both of them can form enolates, they can either A, react with themselves, B, react with something else, and then there's a total of like 4 different products, and that's not even including stereoisomers. So we typically like to stay away from undirected aldol reactions in synthesis because there's no way to isolate one of those products over everything else. So in synthesis, you definitely want to do directed. So not useful, I'll say, in synthesis. All right. Okay. The next topic is thermodynamic versus kinetic control. All right. So the first thing I want to do is just give you guys some conditions to memorize. So thermodynamic control is any time you have an aqueous base or LDA in less than 1 equivalent. All right. And I'll talk about why that is in a second. In kinetic control, it's when LDA is greater than 1 equivalent, all right? So if I see some sort of aldol reaction and I see either sodium hydroxide, potassium hydroxide, or LDA in less than 1 equivalent, I know that I'm under thermodynamic control. When we're under thermodynamic control, we are going to form a beta-hydroxy carbonyl molecule, and then that beta-hydroxy carbonyl is going to be dehydrated to form an alpha-beta unsaturated carbonyl only if alpha protons are available. All right, I know that was a lot, so rewind this if you have to hear that again. Under thermodynamic control, we are going to originally form beta-hydroxy carbonyl compounds. But if there are hydrogens on the alpha position left over, I can dehydrate that hydroxyl group to form an alpha-beta unsaturated carbonyl. And that's a very, very stable molecule because we just generated something that is in conjugation with the carbonyl. All right, so I would definitely know the term alpha-beta unsaturated carbonyl. Under kinetic control, we have LDA greater than or equal to 1 equivalent, and we do not observe that dehydration step that we saw with thermodynamic control. Instead, we're just going to stay at the beta beta hydroxycarbonyls, which I wrote over here, remain at the beta hydroxycarbonyls. And this should make sense. So thermodynamic control, thermodynamics, think back to Chem 1 or Chem 2. Thermodynamics is all about stability and how stable things are. So it makes sense that I'm going to form a heavily conjugated molecule by doing that extra dehydration step. Under kinetic conditions, kinetics was all about rates of reactions and how fast things occur. So I'm not necessarily concerned with stability in terms of kinetics, I'm just concerned on what's going to form the fastest. And what forms the fastest is that first step of just forming that beta hydroxycarbonyl. Alright, so now we're going to just take some time to practice and figure out like how we can classify these reactions. So we're just going to use the terms uncrossed, crossed, directed, undirected, and thermodynamic versus undynamic control to label these reactions and, get some good practice with that. So the first thing I do is the control that it's under. So if I see LDA is greater than 1 equivalent, I immediately know that I'm under kinetic conditions. So I can say that this is a kinetic reaction or under kinetic control. The next thing I want to look at is, do I have two of the same molecule or do I have two different molecules? Well, we have this ketone as our starting reagent, and then we have benzaldehyde. So I don't expect, you're not going to be tested on these common names, but I think benzaldehyde is something you guys should know. It's just an aldehyde directly attached to a benzene. And clearly benzaldehyde is different from that ketone, so we can say that this is also a crossed aldol condensation reaction. So that's crossed, and it's under kinetic control. The next thing is it's directed. So let's just look at the alpha positions to determine if it's directed. So we have alpha 1, we have alpha 2, and over here we have, let's just call it alpha 3. Well, alpha 1 and 2 both have alpha protons, so we can generate the enolate at those positions. So we definitely can form an enolate. I'll just say like enolate possible. Enolate. All right, now let's look at our benzaldehyde. Well, at alpha 3, there aren't any protons, so there definitely is no enolate generated there, so this is a directed reaction. So basically, we can tell that the enolate is going to be formed from that ketone, and in terms of the mechanism, that enolate is going to add into the carbonyl of the aldehyde exclusively. So it's under kinetic control, it's a crossed reaction, and it's directed, because we have one set of mechanistic arrows every time. All right, let's move on to the next one. So when I see an aqueous space like sodium hydroxide, I'm going to think thermodynamic control. That's the first thing. The next thing is, do I have two of the same molecule? Well, yeah, I do. So this is going to be an uncrossed aldol reaction because it's two of the same thing. All right, now this is going to be a little bit tricky. So in terms of directed or undirected, so directed basically means that one molecule has alpha protons and the other one does not. So if I have two of the same molecule and that molecule does have alpha protons, this is going to be an undirected reaction. Okay. So let me just draw this out so maybe that would make more sense. So if I have this molecule and I have it reacting with this molecule, which is the same thing, I have 50-50 chance, even though they are the same exact thing and they give you the same product, who's to say that the first equivalent isn't going to form the enolate at this position and then attack into here? Or who's to say that the second equivalent of enolate is going to form there and attack into this carbonyl? All right? So even though they are the same molecule, both of them have alpha protons, so it is still considered undirected, if that makes sense, because you can have rapid interconversion. You could say that the green one's going to attack the red one, or the red one's going to attack the green one. We just don't know, but you will form the same product no matter what, so it's not going to matter in this situation. All right, so let's look at the next one. So in this case, we see LDA is less than 1 equivalent, so that is something that tells me that it's thermodynamic control, so thermodynamic control. And the next thing is, do I have two of the same molecule? Yes, I do. So this is uncrossed, and the same thing where we just talked about how it's undirected because it's both of those molecules, even though they are the same thing, have alpha protons. All right. All right, finally, I think we're on the last one over here. So I see an aqueous space like sodium hydroxide, so I think immediately I'm under thermodynamic control. Next thing is, do I have two of the same molecule? Well, no, I do not, so I think it's definitely a crossed aldol reaction. And finally, is it directed? Well, here at this alpha position, there are alpha protons, and at this alpha position, there are no alpha protons, so it most certainly is directed. So this one is actually the most ideal because every time the mechanistic arrows are going to be this into there, every time. So we're not going to get a mixture of products. Sure, we might get stereoisomers, but we're not going to get mixtures of major products. And that's how I would classify these reactions. All right? So So let's move on to the thermodynamic control rationale. So yeah, sure, I can memorize all these reagents, sure, you can get it right on the test, but I know a lot of you like to know why things happen. So let me just talk to you about this for a second. So let's just take a second and cross out everything that I don't know. So LDA is something back to Orgo 1 that I know. So let's just say that I have just plain LDA as a reagent, and we know that we have protons that are acidic at either alpha 1 or alpha 2, all right? So in terms of what we remember from Orgo 1, LDA is a bulky base and is limited by steric factors to the side that lacks substituents. So would LDA depronate from alpha 1 or alpha 2? If you said alpha 1, you're right. Because that methyl group is a little bit bulky, LD would prefer to depronate from alpha 1. So the product of that is going to be this molecule. Okay, so now we're going to come back to Orgo 2, and now we're going to consider why the equivalence matters. So it's always assumed that the reagent is one equivalent unless it's stated like there's excess or something like that. But in this situation, we have one full equivalent of ketone. In comparison, our reagent is 0.9 equivalent, so it's not a 1-to-1 ratio that we always see. So we're not going to get, I'm just writing 100%, we are not getting 100% of this molecule because we only had 0.9 equivalents. So the other 0.1 equivalent of, so there is, I'll just write it down here, 0.1 EQ of reagent left. So there's 0.1 equivalent of reagent left over. So really the products of this reaction would be 90% enolate, so it's 90% enolate plus 10% just regular ketone starting material. But now, what happens over time? Even though these are the first products of this reaction, 90% of that enolate, since it's like a lot more than the 10% of the ketone, that enolate can over time deprotonate from the other alpha position. So the mechanistic arrows could look something like that. All right, and since we're generating a more stable enolate, we're forming a more stable product, the equilibrium over time will favor the formation of this enolate. Move over a little bit. Oops. All right, so that makes sense. So we basically have less base than there is starting material. So even though we're going to form a lot of that, I guess you could say kinetic enolate, over time, since there's a little bit more reagent left, we can equilibrate to form the more stable product, and this is what thermodynamic control is. All right, so let's say I had greater than one equivalent. Well, if I had greater than one equivalent, which is under kinetic control, I will form exactly 100% of this enolate. And that means I don't have any more of this left over, so this base isn't going to be able to form a thermodynamic enolate. So that's where the equivalence starts to matter. I hope that kind of made sense on the rationale of why greater than and less than equivalents. I'd like to know why things happen. All right, so let's just do a couple examples of aldol. So again, the first thing we want to do with these reactions is to classify. So the first thing I see sodium hydroxide, so I'm thinking that's thermodynamic conditions. And then the next thing I want to say is it crossed or is it not crossed? Well, this is definitely a crossed aldol reaction because there are more than one product. And the next thing I want to ask myself, is it directed or undirected? Well, it is, let's look at this alpha position over here, and this alpha position over here, so I'll just call that alpha 1, and this is alpha 2. There are alpha protons, so we can form an enolate here, and there are alpha protons, so we can form an enolate there, so it most certainly is undirected. So in undirected situations, we have typically a mixture of products, unless it's the same molecule. All right, so I think this is very useful in the exam. I would definitely label in undirected crossed aldol reactions A and B for the different reagents, because basically we need to keep track of A can add into B, A can add into itself, B can add into A, and B could also add into itself. So let's just draw the major products of this reaction. So I'll draw the mechanism for the first two, and then the other ones I'll just draw on the reagents. So let me just make more room over here. So I'm just going to erase this over here. All right, so let's just do A into A first. So A, we're going to form the enolate at this position. So let me just show the mechanism for you guys. Oops. So this is going to grab a proton and then form that enolate over there. So we now have, all right, and then our reagent is just another molecule of ketone, so it's this. And then that enolate is going to add into the carbonyl. And the product of that is going to be this. All right? And then the O minus gets a proton from the water, because remember we have hydroxide taking off a proton, so we generated water. So this can grab that, and we just formed a beta hydroxycarbonyl. All right, so did we say that these were under thermodynamic or kinetic conditions? Well, we most definitely said that they were thermodynamic, so we would expect a dehydration step. So I do have excess base still laying around. So that base can come and take off that hydrogen, push in that electron, let me fix that arrow, can push in that electron density to form a double bond, and then kick off the hydroxide. And we can do that since it's under basic conditions. We don't have to turn it into a good leaving group. So now we just formed a alpha-beta unsaturated carbonyl. So it looks like that. So this is the end product of this reaction. That's A plus A. So let me just erase all of this mechanism and put back the starting material. All right. All right, so the starting material for, the end product of A plus A looks something like this. All right, so now let's consider A plus B. So we would form the enolate at that ketone over here, and we can add into this carbonyl. So let me just show the mechanistic arrows for that. And you can rationalize, the pronation step and then the subsequent dehydration. So then we're going to form a product that looks like this. Move over. And we would have a phenol group over here. And that's that. So I just wanted to make it noted that we are doing these reactions really fast. So that is the product of A plus B. Just make sure you have your carbon count all in order. All right, so that is that product. So that's A plus B. Let's move this over here. A plus B. So now we need to do B plus B and then B plus A. So B plus B, let's just do that one. So I always like to orient my enolates like this. So, I don't know, that's just personal preference. So that's how I like to orient my enolate, and then I know it's going to add into something that looks like this. So the mechanistic arrows are that going into here, pushing that up. So I would expect a product that looks like this. So a phenol down there, and we are going to form a carbon-carbon bond there. There's going to be a carbonyl, 1 pH. So that's 1, 2, 3, 1, 2 phenol. And yep, that is correct. All right. So that is the product of B plus B. And then finally, let's just do B plus A. This is B plus B over here. And now let's just do B plus A. So B, again, is that enolate. So we're going to show it over here. So pH. And then that's going to add into the ketone. So the mechanistic arrows for that would be something that look like this. And you can rationalize again the pronation step of the alkoxide anion followed by subsequent dehydration. So the end product of that is going to be something that looks like that. Okay, so that is the end product of B plus A. So overall, we have, I'll highlight it, we have this product, this product, this product, and this product. So clearly you can see why we don't like this in terms of synthesis, because we have 4 different products and we can't isolate one or the other. All right, so let's just move on to the next one. All right, so the next one. So we know that we're under thermodynamic conditions, so we can rationalize that we're going to form the more stable or more substituted enolate. So we have 2 alpha positions. We have over here alpha 1, over here we have alpha 2. Alpha 1 is more substituted, so that's the more stable enolate. So we are going to form something that looks like this. And then that enolate is going to react with another equivalent of itself in this manner. All right, so we formed this crazy molecule. Now, the next step is to do a dehydration. So let's look at the alpha position. Do we have alpha protons to do the dehydration? Oh, we really don't have any alpha protons to do that dehydration. So since there are no alpha protons, we can't kick off the beta hydroxyl. So even though this is thermodynamic conditions and we would expect an alpha beta unsaturated carbonyl, we're not going to get that here because there are no alpha protons to continue on that mechanism. So this is actually our final product. And don't forget that we are racemic at this position, so we would have two major stereoisomers of that. All right, so let's just move on to the final one. So this is an intramolecular version of the aldol. So let's just consider all of the alpha positions in this situation. I think that's the most important thing. So we definitely have alpha position 1, alpha position 2, and alpha position 3. So let's just rationalize alpha position 3 attacking into the carbonyl. So if I were to count my carbons, it's 1, 2, 3, 4, 5, 6, 7. That's a 7-carbon ring. That's not going to happen. All right, so we know that's not going to happen. The next thing is we have alpha 1 and alpha 2 left. So if I had alpha 2 adding into that carbonyl and I numbered it, it'd be 1, 2, 3, 4, 5. Oh, a 5-carbon ring could work. So let me just draw the product of that real quick. So a 5-carbon ring, and we have carbon 1, 2, 3, 4, 5. At position number 1, we have a ketone. 2, nothing, 3, nothing, 4, nothing, 5. We did just form an aldehyde. So then that can dehydrate, remember, we're under thermodynamic conditions, to form a molecule that looks like this. All right, so that is the product of the enolate at alpha 2 adding into the aldehyde. Now let's do alpha 1 adding into the other carbonyl. So it'd be 1, 2, 3, 4, 5. Oh, that's another 5-carbon ring. So let's just draw that over here. That's 1, 2, 3, 4, 5. At off of carbon 1, you have an aldehyde. At 2, nothing, 3, nothing. At 4, nothing, 5, you have both a hydroxyl group and a methyl group. And we're under thermodynamic conditions, so we'd expect the dehydration of that. So we'd expect a molecule that looks like this. So be careful in the intramolecular aldols because we want to see all the different possible pathways and all the different combos of products. We'd expect 50-50 in solution that looks like this. All right, I hope that helps. That's all of aldol.